Good morning. My name is Mark Siemens, and I'm with the Department of Biosystems Engineering at the University of Arizona. I'll be presenting this work on behalf of my colleagues, Victor Godinez Jr., Nicholas Barr, and Steve Fenimore. The title of my talk today is A Novel Band Steam Applicator for Controlling Soil-Borne Pathogens and Weeds in Lettuce. Arizona and California produce over 90% of the lettuce crop raised in the United States. Disease control is a major concern of lettuce producers. Sclerotinia, the pathogen which causes lettuce drop, is present in approximately 20% of the lettuce acreage in Arizona and California. Crop losses typically range from 1 to 5%. Another major concern is weed control. Due to the lack of effective post-emergent herbicides, lettuce crops are typically hand-weeded during the growing season. This operation is expensive and labor is becoming increasingly difficult to find. Raising soil temperatures to over 140 degrees Fahrenheit using steam heat is an effective method for controlling soil-borne pests. The technique has been around for over a century and is commonly used in greenhouse and nursery production. Steam-based soil sterilizers for field use are also available. These units are designed to treat the entire soil profile and thus have low work rates and high energy requirements. To overcome these limitations, we propose the use of band steam. Band steam is where steam is injected in narrow bands centered on the seedline. For lettuce, our target is a band 4 inches wide by 2 inches deep. This will minimize energy use and allow for increased travel speed. The objectives of this project were to develop a band steam applicator, determine if the device can raise soil temperatures in a band 4 inches wide by 2 inches deep to levels sufficient to control soil-borne pathogens and weed seed, that is, 140 degrees Fahrenheit for more than 20 minutes. We also wanted to examine the benefit of co-applying exothermic compounds. The idea being that exothermic compounds would release heat when mixed with water or soil and thus reduce energy requirements and increase travel speed. In this study, we are examining 2 exothermic compounds, calcium oxide and hydrogen peroxide. The fourth objective is to evaluate the effectiveness of using steam heat for controlling lettuce drop and weeds in lettuce. The band steam applicator was principally comprised of a steam generator mounted on an elongated bed shaper. As the machine travels, steam is injected into the soil and shaped beds are formed. During development, we tried different methods of injecting steam. One was by knife injection ahead of the throat of the shaper. Another was through cone-shaped ports located on top of the bed shaper. We also utilized injection shanks mounted between the cone steam ports. We found that use of pairs of injector shanks placed 3 inches apart and centered on the seedline worked better than injecting steam ahead of the bed shaper. During the trials, we utilized 2 pairs of injection shanks placed at depths of 1.5 inches and 2.5 inches below the soil surface and 1 cone steam port.
Nick, you got a temperature probe handy? Get a temperature probe. I want to... Maybe I can clip it. That's all right. How deep did you go?
An inch.
Okay, perfect. Ow, that's freaking hot. Whoa, 150. Ow, 151. Dude, we're at 163. Hit the record button.
The band steam applicator was evaluated in trials with iceberg lettuce in Yuma, Arizona. 2 trials were conducted, the first in the late fall of 2020 and the second in the early winter of 2021. Experimental design was a randomized complete block design with 4 replications. Treatments included steam alone, steam plus calcium oxide, and steam plus hydrogen peroxide in an untreated control. Exothermic agents were applied ahead of the bed shaper to promote mixing. Calcium oxide was shanked in at a nominal depth of 2 inches. Hydrogen peroxide was sprayed in a 4-inch wide band ahead of the bed shaper. Prior to steam treatment, Sclerotinia sclerotia were applied to the plots and incorporated to promote disease incidence. Immediately after steam treatment, soil temperature was recorded across the 4-inch wide treated band at depths of 1, 2, 3, and 4 inches using data loggers. This slide shows soil temperature versus time for the second trial at the 2-inch depth for the 4 different treatments. Initially, soil temperatures of the treated plots were about 180 degrees Fahrenheit, which is substantially above the untreated check, where soil temperature was about 45 degrees. After 20 minutes, soil temperatures declined to about 143 degrees Fahrenheit. This exceeded the target temperature of 140 degrees Fahrenheit for controlling soil-borne pests. There were some slight differences between treated treatments initially, but these differences were small, only about 10 degrees Fahrenheit. After 20 minutes, there were no noticeable differences. Another way to look at these data are to plot the highest temperature maintained for 20 minutes at the 4 depths where temperature data were recorded. As shown here, this was done for each of the 4 different treatments. For the steam-treated plots, you can see that the target temperature of 140 degrees Fahrenheit was maintained for 20 minutes at the 1 and 2-inch depths. Temperatures were lower at the 3 and 4-inch depths, but substantially higher than the untreated control. Minor differences were seen between the 3 steam-treated plots. A statistical analysis showed there was no benefit of co-applying exothermic agents as compared to treating with steam alone. There were no significant differences between treatments in mean temperature or the maximum temperature maintained for 20 minutes. The exception to this was that the mean temperature at the 1-inch depth was lower for the steam alone plot. However, the magnitude of this difference was small, only about 5 degrees. These results were not expected, as exothermic compounds should have raised soil temperatures by 10 degrees or more. An explanation for this was that the placement of the compounds was such that they did not completely mix with soil or steam, and thus did not fully react. Use of steam heat significantly reduced weed emergence. As compared to the untreated control, weed density was lowered by over 85%. This translated into a reduction in hand weeding time of more than 3 hours per acre. Despite inoculating the plots with Sclerotinia sclerotia prior to treatment, disease pressure was low in both trials, less than 3%. No significant differences were found between treatments, including the untreated control plot that was not inoculated with Sclerotinia. An unexpected result was that the lettuce in the steam-treated plots appeared to be healthier and more vigorous than those in the untreated plots. These differences carried through to maturity. Steam-treated plots had significantly higher head weights as compared to non-treated plots. Higher average head size translated into a higher percentage of marketable heads and a yield increase of more than 24%. This is significant, as gross revenues for lettuce are about $10,000 per acre. Of note is that this 24% yield increase was found even as compared to the untreated control that was not inoculated with Sclerotinia. Those results are very promising. However, even though only a narrow band of soil was treated, band steaming is still quite slow and energy intensive. To raise soil temperatures from 43 degrees Fahrenheit up to 180 degrees Fahrenheit, a low travel speed of 0.15 miles per hour was required. This translates into a field capacity of 0.05 acres per hour and a work rate of 19 hours per acre. At these speeds, fuel costs were calculated to be $884 per acre. In summary, this project developed a band steam applicator capable of raising soil temperatures in a 4-inch wide by 2-inch deep band of soil to 140 degrees Fahrenheit for 20 minutes. Co-applying exothermic compounds, calcium oxide or hydrogen peroxide, was not effective at raising soil temperatures in this study. Other researchers have found a benefit when co-applying these materials. Better placement or a different design is needed to ensure adequate mixing and a complete chemical reaction. Use of steam heat was effective at controlling weeds and significantly reduced hand weeding time. Due to low disease pressure in the study, we were unable to determine the effectiveness of using band steam for controlling lettuce drop. Using steam heat to disinfest soil increased lettuce yields by more than 24%. Although only a 4-inch wide by 2-inch deep zone was treated, band steaming was still slow and energy intensive. Given the high value of lettuce crops, band steaming may be cost effective if yield increases of 24% can be realized. That concludes my presentation. I'd like to acknowledge USDA NEFA, the Specialty Crop Block Grant Program, the Arizona Iceberg Lettuce Research Council, and Arkema Incorporated for supporting this research.